Before solving numericals on Ising model or paramagnetic system, here we'll just review what Ising model is. So Ising model, basically it's a mathematical model. And it is very useful. It's a very simple system, and it is very useful to study the phase transition. Now, what is Ising model? It's basically a lattice of spins, and each of these spins can have a value of either +1 or -1. So the +1 will correspond to, let's say, parallel, or -1 to perpendicular. Now, the interaction between the spins can be expressed by this expression, minus j summation of sigma I, sigma j, where sigma I or j can have the value of ±1. J is the interaction constant, or sometimes we call it as the exchange integral. Now, this is the energy of the system. Now, if this is the energy of the system when it is not placed in a magnetic field, but if it is placed in a magnetic field, then there will be another term. I'll call it H magnetic. I'll call it H1, maybe H1, which is the energy due to external magnetic field. So this energy we can write as minus mu. B is the external energy term, and mu is the magnetic moment, and it will be summation pi. So depending on whether it is placed in the magnetic field or not, if it is not placed in the magnetic field, then only this term will come. But if it is placed in the magnetic field, then we will have two terms, one from this and one from this. Now, if you pick up any standard statistical mechanics book, then you can learn how to derive the partition function. Here I'll write the partition function for Ising model. So its general formula is 2 cos hyperbolic beta into j to the power n minus 1. But if n is much greater than 1, or n is very large, then we can write it like this: 2 cos hyperbolic beta j into n. So this is the partition function of Ising model. And sometimes in the numerical they might ask the magnetization. So for magnetization we can use this formula. Here F is the free energy with respect to the magnetic field. So if magnetization is asked, then first we have to find out the free energy. Then we have to take the partial derivative of the free energy with respect to the magnetic field. In this question, we are given a system consisting of two Ising spins. Each can take a value of ±1, and the interaction energy is given by this expression, and it is in thermal equilibrium. And we have to, at high temperature limit, the average energy of the system is given by this, and we have to find what is C. So S1 and 2 can take value of ±1. So what we will do is we'll try to find a different configuration possible, and for that I'm drawing a table here. So I'll write here S1, S2 and epsilon. So when this takes +1, energy will be minus j. When it takes -1, +1, it will be plus j. When it takes plus 1, minus 1, it will be plus j. When it takes minus 1, minus 1, it will be minus j. So there is a degeneracy here, we can see. Here a degeneracy of 2 and here degeneracy of 2. Now with this information, we can write the partition function. So it will be 2e to the power minus j beta plus 2e to the power plus j beta. Now we have got the partition function. So we can find the average energy using this formula. Now you can pause the video and do the differentiation, and I'm writing the final answer from the differentiation. So you'll get something j into e to the power minus j beta minus e to the power j beta divided by e to the power minus j beta plus e to the power j beta. This is the expression of the average energy. Now we are asked at high temperature limits. So beta is equal to 1 by kBT. So at high temperature limits, so this one will be much greater, lesser than 1. So we can write the exponential expansion. So I'll consider the first two terms. So j here, it will be 1 minus j beta minus 1 minus j beta. Then in the denominator, I'll get 1 minus j beta plus 1 minus j beta. So 1 plus j beta, sorry. So this two will cancel out and this two will cancel out. So you have minus of j square beta. So the 2 factor will cancel out. So this is minus j square kBT. And it is already given in the question that U is equal to C by kBT. So if I compare these two expressions, C is equal to minus j square. So this is the answer. So it matches with option B. In this question, 3 Ising spins are given, and it is at the vertices of a triangle, and it interacts with each other. And it is given that this is a ferromagnetic Ising interaction. So we have to find the partition function. Now, first we have to write the interaction energy expression. So for ferromagnetic, it is given by J S1, S2, all the possible pairs, S2, S3, and S3, S1. So this is the interaction term. And now we have to find the different possible configurations. So I'll draw the table here. So one here I'll write S1, S2, S3, and this is the energy. So if I choose 1, 1, 1 here, then it will be plus 3J. And if I choose minus 1, minus 1, minus 1, then it will also give plus 3J. What about 1, 1, minus 1? It will give minus J. So like this, you can pause the video and write all the possible configuration. By the way, the number of configuration will be 2 to the power n. So we will have 8 configuration because there are 3 Ising spins. So I will write down all the possible 8 configuration. So another one is 1, minus 1, 1. This will also give minus J. Then you'll have minus 1, 1, 1. This will also give minus J. Then we can have 1, minus 1, minus 1. This will also give minus J. And we can have minus 1, 1, minus 1. This will give minus J. So how many do we have now? We need to have one more. So it will be minus 1, minus 1, 1. So this will also give minus J. So here we can see they all have this same energy, so there is a degeneracy of 6, and here there is a degeneracy of 2. Now we can write the partition function. So z is equal to 2e to the power minus 3 beta j plus 6e to the power beta j. So this is the partition function. So it matches with option B. In this question, we are given 3 Ising spins, and here we have the energy expression, and we have to find the mean value of S3. Now, S3, S1, S2, S3 can take plus minus 1. So we have to find the different combination of these 3 spins and calculate the corresponding energy. So here is the table. Here you can see that when S1, S2, S3 is equal to 1, 1, 1, we get the energy of minus 2j minus h. And similarly, if it is minus 1, 1, then we get plus h. Here also we can see there is a degeneracy. When here we are getting minus h. Here also we are getting minus h. So for minus h energy, there is a degeneracy of 2. Here we have plus h, plus h. This also has a degeneracy of 2. Now we are in a position to write the partition function. So the partition function z will be equal to e to the power minus of minus 2j minus h beta plus, so minus h has degeneracy of 2, so e to the power h beta plus e to the power minus 2j minus h beta plus, and plus h has at the degeneracy of 2, so 2 into e to the power minus h beta. Then you have e to the power minus 2j plus h into beta, and one last term, that is e to the power minus of minus 2j plus h into beta. So this is the partition function. Now this question, the solution of this question is a bit lengthy, but it will be better if you can see in this exponential. If I expand this, I will have one term of 2j beta and another term e to the power h beta. Similarly, if I expand this, I'll have e to the power minus 2j beta into e to the power h beta. So all this term, the argument of the exponent, we can simplify by taking x is equal to 2j beta and y is equal to h beta. This will be handy if you substitute x and y. Now, what about the mean value of S3? Now, here in this S3 column, we can see that S3 can take either plus 1 or minus 1. In this configuration, when it is taking 1, the corresponding energy is this. But here, when it is taking 1, the energy is different, right? So we will write all the possible combinations. So it will be probability of getting 1 into the, here I'll write into 1. Then probability of getting the minus 1 value into probability of getting minus 1. So divided by, the whole quantity will be divided by z. So here it will be, okay, let's take this combination. Then it will be 1 into e to the power minus of minus 2j minus h into beta plus, and we have 1 here, so it will be e to the power minus 2j minus h into beta. Then we have 1 here, so plus e to the power minus h beta plus, then we have 1 more here, so e to the power minus h beta. This expression is for this term, the first term inside the square bracket. Similarly, we can write for the -1 combination. So maybe, okay, here plus, sorry, I'll use a different color so that it is visible. Here you'll have minus. Minus is coming because of this. So minus, maybe I'll put inside a bracket here. So here you have this term here. So it will be e to the power h beta. Then you have this term here plus e to the power h beta plus, then you have this term here. So e to the power minus 2j plus h into beta. Then you have last term here. So it will be plus e to the power minus 2j plus h beta. This whole thing will be divided by z. Now, this x and y, if you substitute it here and by doing manipulation, you can get S3 is equal to, you can pause the video and do the manipulation, because you'll be able to take some terms common outside, and you'll get an expression like this: 10 hyperbolic y into cos of hyperbolic x minus 1 divided by cos of hyperbolic x plus 1. Here x is what? X is 2j beta. Now this term inside the bracket, we can again simplify, and we can, this term you can simplify to 10 hyperbolic square into j beta. So if I substitute this, you can get the final expression here. S3 average value will be equal to 10 hyperbolic. Here y is h beta into 10 square, hyperbolic square into j beta. So this is the final answer. The calculation is a bit lengthy, but it's very easy. The only thing is you substitute this x and y, then the calculation will, it will become easy, because there are so many terms. So if I see the options here, then I think option B is the correct answer. In this question, the partition function is given for n Ising spins, and lambda 1 is greater than lambda 2, and we have to find the free energy per spin in the limit n tends to infinity. So partition function is given, so z is equal to lambda 1 to the power n plus lambda 2 to the power n. Now the free energy, we can use the formula minus kBt log of z. So the free energy will be given by minus kBt log of lambda 1 to the power n plus lambda 2 to the power n. So this is the expression of the free energy, but they have given that lambda 1 is greater than lambda 2. So what can I do is, I can take lambda 1 to the power n common outside. So it will be 1 plus lambda 2 by lambda 1 to the power n. So this term, since lambda 1 is greater than lambda 2, I can approximate and take this term to be 0. So now I have minus kBt log of lambda 1 to the power n. So this gives n kBt log of lambda 1. So this is the free energy. under the condition that lambda 1 is greater than lambda 2. Now they are asking free energy per spin. So free energy per spin will be free energy divided by the number of spins. So it will be minus kBT log of lambda 1. So this is the answer. So I think it is matching with option D. In this question, we are given a system consisting of 3 Ising spin, and this is the interaction expression, and we are told to find average energy of the system. Now here S0, 1 and 2 can have possible value of plus minus 1. So we need to find the different configuration and the corresponding energy. So here is the table here. In this table, we can see that for different combination, we have calculated the corresponding energy. And we can observe that for minus 2J, there is a degeneracy of 2. And for 2J, there is a degeneracy of 2. And for 0 energy, there is a degeneracy of 4. Now we can write the partition function. So partition function will be equal to 2e to the power 2j beta plus then 2e to the power minus 2j beta plus 4e to the power 0. So you get 2e to the power 2j beta plus 2e to the power minus 2j beta plus 1. So this is the partition function. Now we are asked what energy. Okay. Now energy, average energy, average energy will be equal to summation of EI GI e to the power minus EI beta divided by the partition function. So if we substitute this, let's start from minus 2J. So minus 2J is the energy. It has a degeneracy of 2. So it will be 2J beta. Then for the energy 2J. So 2J is the energy and we have a degeneracy of 2. So e to the power minus 2J beta. And the last term, the energy is 0. So whatever we multiply, it will give 0 divided by. So 1 plus 2e to the power plus 2j beta plus 2e to the power minus 2j beta. Now this is the expression, but in the options they are given in the form of hyperbolic function. So what we can do is E is equal to, if I take minus 4j common, then I will get e to the power 2j beta minus of e to the power minus 2j beta divided by, and here what we can do is we can, in this term we can take 2 common, then it will be here 4 should be there, sorry, here 4, yes, here 4 should be there, so I can take 2 outside. It will be 2 plus e to the power 2j beta plus e to the power minus 2j beta. So this one I can cancel out. Now this term I can write as sine hyperbolic function, and this term I can write as cos hyperbolic function. So it will be minus 2j sine hyperbolic of 2j beta divided by, so 1 2 fact, okay, here it should be 4 because so when we convert to a sine hyperbolic function, 1 2 factor will come and 1 2 factor also will come here. So this one will be cos hyperbolic 2j beta. So here we can cancel this 2 and we will be left with 2 here. So this option I think it's option D. Option D is the correct answer. Here we are given n non-interacting classical spins, and each spin can have value of -1, 0, and 1, and it is placed in a magnetic field, and this is the interaction energy term. And if m is the magnetization, then we have to find out this expression, that is 1 by n, partial derivative of m with respect to h. H is the magnetic field in the temperature disk. Now, so sigma can have plus, -1, or 0. So there are 3 possible values. So first thing we'll do is we will find all the possible combinations. So sigma h, okay, when sigma is +1, okay, when sigma is +1, it will be minus mu b h. And when sigma is 0, it will be delta. And when sigma is -1, it will be mu b h. So these are the 3 energy values. Now, using this information, we can calculate the partition function. So partition function will be equal to, this is for single particle. So partition function of, single spin. So partition function will be e to the power beta mu b h plus e to the power minus beta delta plus e to the power minus beta mu b h. So this is the partition function for a single particle. Now what can I do is I can use these 2 terms and express in the form of, not this 2 term. I can use this term and write in the form of cos hyperbolic function. So I can write 2 cos hyperbolic beta mu bh plus e to the power minus beta delta. So this is the partition function for a single spin. Now for n spin, it will be the power of this. So we have 2 cos hyperbolic beta mu b h plus e to the power minus beta delta to the power n. So this is the partition function for n spin. Now we are told to find out the magnetization. So first we need to find the free energy. So free energy is given by minus kBt log of z. So this will be equal to minus n kBt log of 2 cos hyperbolic beta mu bh plus e to the power minus beta into delta. So once you find free energy, and we have already discussed how to find magnetization from free energy. So magnetization will be equal to negative of the derivative of the free energy with respect to the magnetic field. Here the magnetic field is H. So when you take this derivative, you will get an expression something like this. You'll get an expression n mu b into e to the power beta h mu b minus of e to the power minus beta mu b h divided by e to the power beta mu h plus e to the power minus beta mu b h plus e to the power minus beta delta. So you'll get a term like this. Now what you have to do is, here they have given h tends to 0. magnetic field tending to 0. So if H tends to 0, then this term and this term and this term and this term, it will be very small. So you need to do the expansion of exponential. So when you do the expansion, you can simplify the term and you will be getting an expression like this. M is equal to n mu b square n mu b square beta h by 2 plus e to the power minus beta into delta. Okay, so then they're asking 1 by n del m of del h. So if you differentiate this term, finally you'll be getting 2 mu b square beta divided by 2 plus e to the power minus beta into delta. So this is the answer. Here, please note that this H tends to 0, I have already implemented in the expression of the magnetization. So the correct answer is, I think, option D. No. Correct answer, sorry. The correct answer is option B. Here we are given an ensemble of non-interacting spin of minus half particle, and it is in contact with a heat bath at temperature T, and it is subjected to an external magnetic field. And each of this particle can be in one of the quantum states of energy plus minus epsilon naught. And here, please note here that the mean energy per particle is given. It is minus epsilon by 2, and we have to find the free energy per particle. So the first thing which we can do is we will write the partition function for a single particle. So for a single particle, the partition function will be e to the power minus epsilon naught beta plus e to the power epsilon naught beta. Now, so this we can write in the form of 2 cos hyperbolic epsilon naught beta. Now for n particle, it will be z1 to the power n. So z, it will be 2 cos hyperbolic beta epsilon naught to the power n. Now we have got the partition function. The next thing we have to do is we are told to find the free energy per particle. But to solve this, here they have also given the mean energy per particle. So we have to find out the energy also, because it will lead to simplification of the expression. So this one we can calculate by minus ln z by beta. So you can pause the video and you can solve it. So this you'll get minus n epsilon naught, then hyperbolic epsilon naught beta. So if I bring the n this side, it will be minus epsilon naught, then hyperbolic epsilon naught beta. Now in the question, it is given that u by n is equal to minus epsilon naught by 2. So if I equate with this, it will be minus epsilon naught, then hyperbolic epsilon naught beta. So here epsilon naught I can cancel, minus I can cancel. So here I'm getting one expression that then hyperbolic epsilon naught beta is equal to 1 by 2. This will be using while calculating the free energy per particle. Now let us come back to this free energy. So free energy per particle, to calculate this, we can use the expression F is equal to minus k beta t log of z. So if I substitute the partition function expression, I will be getting minus n k b t log of 2 cos hyperbolic beta epsilon naught. Yes. Now if I bring this n this side, it will be free energy per particle. It will be minus k beta t log of 2 cos hyperbolic beta epsilon. Now see, here we need the information of this cos hyperbolic beta epsilon naught. This we can find it from here by using basic trigonometry. So by using basic trigonometry, you'll find that if tan hyperbolic epsilon beta is equal to 1 by 2, so cos hyperbolic beta epsilon naught will be equal to 2 by root 3. So this you can substitute it here. At the same time, we need the information of k beta t. So to find out this k beta t, what you can do is you can use the same expression. From this expression, you can find out the value of k beta t, and it's a simple mathematics. So from this, you can find that k beta t is equal to 2 epsilon naught by log of 3. So this information we will substitute it here. So if we substitute this to information, finally you'll get free energy per particle will be equal to minus 2 epsilon naught log of 4 by root 3 divided by log of 3. So this is the answer. And I think it is matching with option A. Here we are given a collection of non-interacting spin, and it is kept in an external magnetic field B, and Hamiltonian is given here, and we are told to find the minimum value of this, for which the mean value will be greater than or equal to 1 by 3. Now, the spins can have two values. So the SI can have plus or minus 1. So H can have either plus or minus mu p. So using this information, we can write the partition function. So partition function will be e to the power minus mu b divided by kbt plus e to the power plus mu b by kbt. So this is the partition function. Now, the probability for the spin to be in plus 1 will be given by e to the power minus mu b kbt divided by the partition function. Similarly, for minus 1, we'll get e to the power mu b by kbt divided by the partition function. Now, using this information, we can find the average value for a single particle. Not particle, but for a single spin. So the average value will be equal to the plus 1 value into probability for plus 1 plus then the minus value, then the probability for minus 1. So we can substitute the expressions on the left hand side, and when we solve this, we will get minus tan hyperbolic mu b by kbt. Now this is for single particles. So for n particles, for n spins, it will be minus n. For n spin, it will be minus n then hyperbolic mu b by kbt. Now we have got the average value of SI. Now they are asking average value per spin, right? So if I want to find per spin, it will be SI for n particle divided by n. So it will be minus 10 hyperbolic mu b by kbt. Now we are given a condition that the average value should be greater than or equal to 1. So what we can do is we can substitute equal to 1 by 3 condition here, the minimum value. So here from this expression we are getting 10 of hyperbolic mu b kbt is equal to minus 1 by 3. Now using the basic trigonometry, you can solve this and you will get mu b by kbt is equal to 2 log of 1 by 2. So this is the answer. So I think it is matching with option B. In this question, we are given a paramagnetic system and it is in thermal equilibrium and it is kept at a constant magnetic field. We have to plot the average magnetic moment as a function of this quantity. Now we already know that if a dipole is placed in a magnetic field, the energy is given by plus minus the magnetic moment into the magnetic field. So what I'll do is I'll just denote this by plus minus epsilon. So now I can write the partition function for a single dipole. It will be e to the power beta epsilon plus e to the power minus beta epsilon. Now for n particle, okay, this one we can simplify as 2 cos hyperbolic beta epsilon. Now for n particle, it will be 2 cos hyperbolic beta epsilon to the power n. Now we have got the partition function. So we can find the free energy. So free energy is equal to minus kbt log of z. So this is equal to minus n kbt log of 2 cos hyperbolic beta epsilon. Now we have got the free energy. So from free energy we can find the magnetization. It is equal to the derivative of the free energy with respect to magnetic field. Now you can pause the video and do the derivation. I'm writing the final expression here. So it will be equal to n mu b tan hyperbolic of beta mu b into magnetic field. Now we have to plot magnetization versus kbt mu b p, and this is nothing but 1 by beta mu b into p. Now to plot this, what we will do is we will try to see the two extreme limit of the variable on the x-axis. So one here I will take high temperature and low magnetic field. So high temperature and low magnetic field means at the higher value of the x-axis. So in that case, this 10 hyperbolic beta mu b into b, so this quantity, it is, I can rewrite this one as mu b into b divided by kbt. So this quantity, this argument of this 10 hyperbolic is very much less than 1. So we can use the exponential expansion and we will get m is equal to n mu b into beta times mu b into b. So in this limit, in when this quantity is very large, so this quantity will be very small. So if this quantity is very small, then the magnetic moment will tends to 0. So here I'll write here in this limit mu will tends to 0. In the second case, I will take low temperature and high magnetic field. So here low temperature and high magnetic field means towards the lower value of this graph of this x-axis. So in that limit, the tan hyperbolic beta mu naught b will be approximately equal to 1. So magnetization will be approximately equal to n times mu b, which is a constant. This is a constant. Now from this two extreme limit, we can see that when the x-axis value is very high, it will tend to 0, and when it is very less, it will tend to some constant value. So the graph will look something like this. Here we are given a Hamiltonian of 3 spins, and we are told to find the canonical partition function. So S1, 2, 3, they can have plus minus 1. So we need to find a different configuration and find the corresponding energy. So here is the possible combinations and the corresponding energy. And here we can see that for 2j there is a degeneracy of 2, and for minus 2j there is a degeneracy of 2, and for 0 there is a degeneracy of 4. So we can write the partition function as z is equal to 2e to the power minus 2j beta plus 2e to the power 2j beta plus 4 into e to the power 0. So this is 2e to the power minus 2j beta plus 2 e to the power 2j beta plus 4. So here we can take 2 common outside. So 2j beta plus e to the power 2j beta plus 2. And the expression inside the square bracket we can write as a plus a square plus b square plus 2ab. So this will give 2 cos hyperbolic j beta whole square. So, and sorry, one more 2 should be there. So you'll have like this. So I think option B is the correct answer. Now with all the techniques which we have learned till now in all the videos, now I will discuss some other variants of partition function problem where they have used some concept of classical mechanics and quantum mechanics. So here we are given n classical particles in 2-dimensional square box of side L, and if the total energy is E, then we have to find entropy apart from the additive constant. So the first thing we have to do here is we have to write the Hamiltonian. So Hamiltonian will be px square by 2m plus py square by 2m. Now, compared to the previous technique of calculating partition function, here we will be using a concept called the partition function is also equivalent to the total volume in the phase space. So if I want to calculate the partition function of a single particle, then we will use the phase element. Since it is 2-dimensional, it will be 1 by h square. Then we will integrate this minus px square beta by 2m dpx then e to the power minus py square beta by 2m dpy, and you have integration of dx and dv, dx and dy. So this term we will get an expression of L square. So this is the equivalence of the volume element in 2 dimension. Now for the other two term, we can use the integration trick. So this will be equal to pi by beta by 2m, and the second integral will be equal to pi by beta by 2m into L square. So here I can write the final expression. It will be 2 pi m divided by beta square h square L square. So this one I can write as 2 pi m kb t L square by h square. Now this is the partition function for the single particle. Now if I want to find the partition function for n particles, then let me use a different color here. Then z will be equal to z1 to the power n, and here we'll be dividing by n factorial, the Gibbs correction factor. So here it will be 1 by n factorial 2 pi m kbt h squared to the power n. So this is the partition function. Now once we get the partition function, we can find the free energy. So free energy will be given by minus kbt log of z. Now you can pause the video, and here I'll write the final expression. So it will be kt n log of n minus. Here while calculating this, you have to use the formula that log of n factorial is equal to n log n minus n. So here you'll get ktn minus of nkt log of L square E divided by n into some constant C. Now later on you'll find that they have taken this constant C to be equal to 1. Otherwise none of the options will be matching. So if I take this the constant factor C to be equal to 1, so now we have got the free energy. Now to find the entropy, we know that U is equal to Ts, or you can use the free energy formula, that will be better. So F is equal to U minus Ts. So S is equal to U minus F divided by T. Now F we have calculated. U, it is already given in the equation. It is equal to E. So you can substitute U and F, then you'll be getting an expression like this. 2nk minus kn log of n plus nk log of L square E divided by n. I have taken the constant factor to be equal to 1. So now this term it is a constant factor. Now this term I can absorb it here. So if you absorb that, you'll get 2nk plus of 2nk log L by n root over E. So this is the answer they are asking for. So it matches with option C. Now in this question we are given rotational energy levels given by this expression, and we are told to find the Helmholtz free energy at low temperature limit. So from atomic and molecular physics we know that for rotational energy levels there is a degeneracy. So first here I'm writing the energy expression. So it has a degeneracy of 2L plus 1. So using these two information, I can write the partition function. It will be summation of L0 to infinity 2L plus 1 into exponential minus beta h bar square L into L plus 1 divided by 2I naught. So if I substitute L is equal to 0 here, then I'll get like this 1 plus. Now the summation will run from 1 to infinity 2L plus 1 e to the power minus beta h bar square L into L plus 1 divided by 2I naught. Now we have got the partition function. Now the free energy will be given by minus kBT log of Z. So it will be equal to minus kBT log of 1 plus the summation from L is equal to 1 to infinity 2L plus 1 into exponential minus beta h bar square L into L plus 1 divided by 2I naught. Now we are asked in the limit at low temperature limit. Now if I write X as e to the power minus beta h bar square L into L plus 1 by 2I naught. Now in the low temperature limit, beta will be very high, and here we have beta and it is negative. So using that information, we can use the expansion of log 1 plus x. This is approximately, see in the question they have asked approximately. So this one will be equal to x minus x square by 2 and it's so on. So we'll consider only the leading order term. So we can approximate the free energy as minus kBT into, now here please note that here there is a summation term. So we'll consider the first term. First term means L is equal to 1. So when L is equal to 1, 2L plus 1 will be 3. So here a factor 3 will come. Then e to the power minus h bar square. Then in place of L we can substitute what? 3. So here, sorry, in place of L we can substitute 1. So it will be 2 divided by 1 more beta will be here, then 2I naught. Yes. Now, so this is equal to minus 3 kBT e to the power. So this 2 will cancel out. So e to the power minus h bar square into kBT I naught. So this is the answer. So I think it is matching with option D. In this question, it's a 2-electron system which is in thermal equilibrium and they can occupy 2 sites. And the configuration energy is given by this term, and S denotes the spin of the electron, and when the 2 electrons are occupying different site, it is given by this expression. But if they are occupying the same site, then the energy is given by U, and U is equal to 10J, and we have to find the probability that the system will be in the first excited state. So this question consists of two concepts. One is the partition coefficient concept, and other one is the addition of spin angular momentum concept. So there are two electrons and they are spin half particle. So S1 and 2 can have half. So we already know from quantum mechanics that this can lead to two type of state. One is the triplet, where S is the net spin angular momentum will be 1, and what is the singlet, where it will be equal to 0. And from quantum mechanics, we also know that S1 and S2 dot is equal to S plus 1 minus S1 plus 1 minus S2 plus 1 by 2. So we need this concept. Now, also, the degeneracy is given by 2s plus 1. 2s plus 1. So in this case, we have a degeneracy of 3. In this case, we have a degeneracy of 1. Now, using this concept, we can calculate the energy. So for singlet, if you substitute S1 and S2, then you'll get U is equal to J by 4. And for triplet, and for singlet, you'll get U is equal to minus 34J. Now, if we compare this to energy, the singlet is the lower energy state, and the triplet is the excited energy state. Now let us write the partition function. So partition function Z is equal to 3 for the singlet degeneracy e to the power minus beta J by 4 plus, and now we'll write for the singlet. So e to the power 3 beta J by 4. Now, in addition to these two terms, there is one information given here, that if the electrons occupy the same site, then it will have an energy of U. So both the electrons will be either in the lower energy state or in the higher energy state. So, and U is given by 10J. So because of this, there will be an additional term 2e to the power minus 10J beta. Now we have got the partition function. Now the probability that it will be in the higher excited state, so the probability will be given by 3e to the power minus beta J by 4 divided by the partition function. So it is 3e to the power minus beta J by 4 plus e to the power 3 beta J by 4 plus 2 10e to the power, this will be e to the power minus 10J beta. So this is the answer. Now, if we see the options, I think option B is the correct answer. In this system, we have a quantum system whose Hamiltonian is defined by this, and SI, that is Sx and Sz, they are expressed in terms of Pauli matrices, and in the condition J much greater than lambda, we have to find the leading order correction in the partition function. Now here, this Hamiltonian, it consists of two terms. One is the original one, and one is the perturbation. Now, the first thing we have to do here is, okay, Hamiltonian is given by J S Z plus lambda Sx. Now, this lambda Sx is the perturbation. So what we'll do is we'll substitute the Pauli spin matrices. So it will be J, the Sz we can write as minus 1 0 plus lambda 0 1 1 0. Now if we sum these two, we will get j lambda here and minus j. Now this is the Hamiltonian matrix. Now from the Hamiltonian matrix, we'll find the eigenvalue. So you can pause the video and you can solve for the eigenvalue. So the eigenvalue will be plus minus root over lambda square plus j square. Now we have the energy here. So let me denote the energy by E. E is equal to plus minus h bar. H bar by 2. Now what we can, okay, so h bar by 2 lambda square plus j square to the power half. So what I'll do is, I'll take j common. So it will be plus minus h bar by 2 j 1 plus lambda square by j square to the power half. Now since lambda is much lesser than j, so we can approximate this as h bar 2 j 1 plus lambda square by 2j square. So with this approximation, we have got the energy. Now from this energy, we can calculate the partition function. So z will be equal to e to the power. So I'll call this one as plus minus e. So minus e plus beta and e to the power plus e minus beta. So when you substitute this value, you can do the simplification, and finally you'll be getting an expression e to the power minus beta h bar j by 2 plus e to the power beta h bar j by 2 plus beta h bar square lambda square divided by 2j into 2 of sine hyperbolic j h bar by 2 kBt. So this is the expression. Now in this expression, this term is due to the perturbation. So this is the answer. So if I check, so instead of this beta, you can write 1 by kBt. So if I try to match, okay, option D is the correct answer. This is the last question in this partition function video series. Here we are given Hamiltonian. In the Hamiltonian, we have the two kinetic energy term and we have the potential energy term, but here Q1 and Q2 is coupled. So we are told to find the value of the partition function. So the partition function will be equal to integration of e to the power minus p1 square beta by 2m dp1 and integration of e to the power minus 2 p2 square beta by 2m p2 and integration of e to the power minus, so I'll write here double integral, so k q1 square plus q2 square plus 1 by 4 q1 q2 beta into dq1 and dq2. Now this integration, we know it will be pi by beta by 2m. This one also will give root over pi by beta by 2m. But for solving this integration, here we have this coupling term. So what you can do is, first you take this q1 square and this 1 by 4 q1 q2, Then you integrate with respect to Q1. Then the answer will have Q2 terms. Then you integrate with Q2. Then you integrate with respect to Q2. So if you do that integration, you'll get pi by k beta root over 64 by 63. So if you compile all this, you'll get 2 pi square m divided by k beta square root over 64 by 63. So this is the answer. So it is matching with option D. Thank you everyone for watching this video series on partition function.